Assalamu alaikum. This is the second session of the first lesson, energy. At the end of this part, you are going to be able to define an energetically isolated system, define the total energy of the system, define the internal microscopic energy and the mechanical energy of a system. Let's remember what we have mentioned in the first video. First, we said work done by a constant force is given by the scalar product of F with AB vector. Work done by weight equals to mg, h initial minus h final. If alpha is an acute angle between the force and the displacement, the work is positive and it is motive. If this angle is obtuse, then the work is negative, thus resistive. If the force is perpendicular to the displacement, then the work is null. The average power is the variation of energy with respect to time, and finally the instantaneous power is the scalar product of the force with the instantaneous velocity vector. What is energy? An object possesses energy if it's able to do work. In other words, energy is the reserve of work. It has a symbol, E or W, and its unit is joules. What are the different forms of energy? Energy has different forms: thermal, electrical, chemical, mechanical, nuclear, radiated, and other forms, but mainly we're going to talk about mechanical energy in this lesson. Energy isolated system. If the system doesn't exchange any form of energy with the surroundings, its total energy is conserved. The total energy of the system remains constant from the start to the end of any transformation. The total energy then is the sum of macroscopic energies and microscopic internal energies. Microscopic energy or the internal energy. The internal microscopic energy U is the sum of the microscopic potential energies and the microscopic kinetic energies. Microscopic potential energy is due to the interaction between particles inside a system, while the microscopic kinetic energy is due to the thermal agitation of a system. The macroscopic mechanical energy. The mechanical energy of the system at any instant is the sum of its kinetic energies and potential energies, while the potential energy is the sum of the gravitational potential energies and the elastic potential energies. Then we say that the mechanical energy is given as kinetic energy plus gravitational potential energy plus the elastic potential energy. We can say that the total energy is the sum of internal energy, the microscopic, and the mechanical energy, the macroscopic. The macroscopic one is the sum of kinetic energy and the potential energy, while the potential energy has two forms, the gravitational potential energy and the elastic potential energy. Kinetic energy. The kinetic energy is the energy possessed by the system due to its motion. So, this energy is due to the speed of a system. For a particle of mass m moving at speed v in a translational motion, the kinetic energy is given by half mv squared, where kinetic energy is measured in joules, mass in kilograms, and v in meters per second. Now, if the particle is at rest, the kinetic energy will be zero. And if the particle is in motion, then the kinetic energy is positive all the time, since it depends on mass and the square of its speed. Note that we should use the SI units, so to convert from gram to kilogram, we should divide by 1000 or multiply by 10 to the power minus 3. And from kilometers per hour to meter per second, we should divide by 3.6. For a system of particles, the kinetic energy of a system of n particles is simply the sum of the kinetic energy of each particle. But for a rigid system, in translation, the speed will be constant, the same for all particles. So we can take half v squared as common, and m1 plus m2, m3 will be the mass of the whole system. So the kinetic energy is just half m of the system times v squared. For a rigid system in rotation, the particles in the system do not have the same linear speed, but they have the same angular speed theta prime. So this kinetic energy will be the sum of the kinetic energies of each particle, half m1 v1 squared, half m2 v2 squared, etc. Keeping in your mind that there is a relation between the linear speed and the angular speed, which is v equals to r theta. Replacing each speed v1, v2, vn by its relation with theta prime, we will find that the kinetic energy of the system can be written as half m1 r1 squared theta prime squared plus half m2 r2 squared theta prime squared, etc., keeping theta prime the same because it is the same for all particles. At the end, we can take half theta prime squared common. Note that mr squared is the moment of inertia for a particle, so finally we can say that the kinetic energy of the system can be written as half I theta prime squared, and I here is the moment of inertia of the system of particles. Let's solve this application. A uniform and homogeneous disk of mass m equals to 2 kilograms and radius r equals to 20 centimeters rolls down an inclined plane at an instant t1. The speed of its center of mass is 1 meters per second, and the angular speed about its axis is 5 radians per second. Given the moment of inertia of this disk as m r squared over 2, calculate at the instant t1 the translational kinetic energy of the disk. The center of mass of this disk is making translation, so its kinetic energy is half mvg squared. Replacing the mass and vg by their values, the answer is 1 joule. The rotational kinetic energy of the disk. The disk is rolling, so its kinetic energy is half I theta prime squared, where I is the moment of inertia of the disk, mr squared by 2. Replace the mass, the radius, theta prime by their values. The answer is half joule. The last part, calculate the total kinetic energy of the disk. Here we have two types of kinetic energies, translational and rotational. The sum of these two kinetic energies gives the total kinetic energy, and it's 1 plus 0.5 equals to 1.5 joules. Gravitational potential energy. The gravitational potential energy of a system is proportional to its mass and its height from the reference level of gravitational potential energy. Its relation is given by mgh, where E in joules, mass in kilogram, and h in meters. The gravitational potential energy of a system is due to the height from the reference level, and the reference level of a gravitational potential energy is the horizontal plane in which EPG equals to 0 joules. Consider a particle of mass m moving down a curvilinear path A, B, C, D, where the horizontal plane passing through point B and D is the gravitational potential energy reference. In this case, at point A, the ball is above the gravitational potential energy reference, so the potential energy at A is positive. At points B and D, the ball is on the gravitational potential energy reference level, so the potential energy at these points is 0. At point C, the ball is below the gravitational potential energy reference level, so potential energy at this point is negative. Consider this application. Application 2, a solid mass of mass m equals 2 kilograms is released without initial velocity from a point A along a rectilinear track AB equals to 100 centimeters, making an angle 30 degrees with the horizontal as indicated in the adjacent figure. Neglect all frictional forces and take G equals 10 meters per second squared. First, calculate the gravitational potential energy stored in S at point A. The gravitational potential energy of the system at point A is given by mgh, where height A is opposite to the angle 30 degrees. So we can write it as mg AB sine alpha, since h is not given, and replacing AB by its value and the angle alpha, so the answer will be 10 joules. The second part did use the mechanical energy at A. They said that it started without initial velocity, so the kinetic energy initially is 0. And finally, the mechanical energy at point A is simply the gravitational potential energy only, which is 10 joules. Given the mechanical energy of S at B is 10 joules, calculate the speed of S at B. The mechanical energy of S at B is kinetic energy at B plus the potential energy at B, which is gravitational. And the horizontal plane containing B is taken as the reference level for a gravitational potential energy. So in this case, the gravitational potential energy at B is 0. Then the mechanical energy at B is just the kinetic energy, which is half m VB squared, which is 10 joules. VB squared in this case is 10, and VB equals to radical 10 meters per second. Elastic potential energy. Elastic potential energy is due to the deformation of an elastic object, either elongation or compression of a spring. Examples like a stretched arc, a compressed or elongated spring, or a bouncing ball. Consider a spring at equilibrium of length L0 elongated to a length L, where delta L is the elongation of this spring. The elastic potential energy stored in the system as spring is given by the relation half K delta L squared, where EPE is given in joules, K is the stiffness of the spring given in Newton per meter, delta L in meters. Delta L is the elongation or compression of the spring from its initial length L0. A force of tension is applied to this spring. Due to Hooke's law, the absolute value of T is given as K, absolute value of delta L. At equilibrium, the tension is 0 and the elastic potential energy is half K delta L squared. It is 0 since there is no elongation, no compression. In case of elongation, the length increases, expression of elastic potential energy, half K delta L squared, and it is positive. In the case of compression, L decreases. Here we have half K delta L squared, and also it is positive since we are squaring x in both cases. Let's solve an application on the elastic potential energy. A solid S of mass m equals 200 grams is connected to a massless spring of unjoined turns and constant K equals 20 Newton per meter. S can move on horizontal ray. We displace S from its equilibrium position. The spring is then compressed by a distance OA equals 10 centimeters. Calculate the mechanical energy of the system at T equals to 0. The mechanical energy is all the time the kinetic plus potential. But take here the gravitational potential energy reference to be the horizontal passing through A and O. So there is no gravitational potential energy. And at T equals to 0, the speed of the spring or the mass is 0. So the kinetic energy is 0. Then the mechanical energy equals to potential energy elastic equals to half kx squared. By replacing the values, it is simply 0.1 joules. Torsion potential energy. A torsion wire with torsion constant C is displaced by an angle theta from its equilibrium position. So it possesses a torsion potential energy, which is a kind of elastic potential energy. Its relation is given by half C theta squared, where theta is expressed in radians, C is expressed in a Newton meter per radians, and the E potential energy is given by joules. To solve an application, a uniform homogeneous thin rod is connected from its midpoint to a vertical torsion wire of torsion constant C, given 0.02 Newton meter per radians. AB is rotated horizontally from its equilibrium position by an angle θ0, then released without initial velocity. Neglect all frictional forces and given the moment of inertia of this rod as 5 times 10 exponent minus 3 kilograms meter squared. At an instant t, the angular abscissa of the system is 30 degrees, where its mechanical energy is 0.01 joules. Calculate the angular velocity theta prime of the system rod at this position. The mechanical energy of the system is kinetic plus gravitational potential energy, which is 0 because it is passing through the gravitational potential energy reference, plus the torsion potential energy. Then the mechanical energy is half I theta prime squared because the system is in rotation, plus half C theta squared because we have torsion wire. By calculation, we can find that the mechanical energy, which is given as 0.01, equals to half I is 2.5 times 10 exponent minus 3 theta prime squared plus 2.74 times 10 exponent minus 3 because pi over 6 is taken in radians, where you should use pi as 3.14 radians. After calculation, theta prime is given as plus or minus 1.704 radians per second, angles in the two sides. From the first video, we have said that the work is the scalar product F dot AB vectors. The average power is the variation in energy per unit time. The work done by weight is mgh initial minus h final. The power is given by F dot V instantaneous. From this video, we can sum up the following. When doing a work, energy is transferred from an object to another or transformed from one form into another form. The total energy is the sum of the macroscopic energies and the microscopic energies. The mechanical energy is the sum of potential energies and kinetic energies. The potential energy is the sum of gravitational potential energies, which is plus or minus mgh, and the elastic potential energies half kx squared. The translational kinetic energy of a system is given by half mv squared. The kinetic energy in rotation is half I theta prime squared. Finally, the torsion potential energy, which is elastic, is half c theta squared. Thank you for watching. This is the end of the second part of the first lesson, energy.